So data handling instructions. Some of them we already used. PLC instructions for moving data from one spot to the other. They say register. Like I said, this guy don't use the term register correctly. We're going to talk about stacks. We've already talked about that a little bit. Moving data between tables, use PLC for numbering system conversion. So reading, storing, retrieving, and writing data on ports and data files, moving or copying data to another data file, converting data to a different numbering system, performing a logic operation on data. I don't know what the last one means there. Oh, I know what it is. So these are our instructions. We have the move instruction. It's called move, but technically it's a copy. They call it a move instruction, but all it's doing is moving, is copying information from one location into another location. Right, copying a source to a destination. Move with mask. We're going to look at first in, first out. First in, first out load. First in, first out unload. Last in, first out. First in, last in, first load. Last in, first out unload. Copy. Fill. Convert BCD to convert binary to BCD. Convert BCD to binary. Convert from radians to degrees, which we're not going to get into that very much. You're not going to use that very much. And then we'll look at the instruction set that's available for us and see what other things that we might have available. Index register. So we're going to look at what we call index address. We've already talked about it a little bit. So inside our PLC, let me bring up RS Logix 500. And I don't have this guy hooked up, so I'll. So here's our project tree on the left. System file 0 and 1. These are your system files. And the first one we're going to do, our main program is called ladder 2, or file number 2, right? Everybody okay? Controller properties. This shows you basically which communication standard the program was saved under. So if I wanted to save the way I connected to the PLC, this is the way I would come up and check it right here, right? I know the other day I couldn't figure out how to do it, but I did find that. So here's our instruction set across the top. We've bit instructions, timer counter instructions, input output instructions. Here's, by the way, input output instructions. Compare instructions. Computer math, logic, file and miscellaneous. Program control, ASCII convert, which we might not have time. High-speed counters. I might set one of these up for y'all before this is over, just to show y'all. We talked about a high-speed counter. What is a high-speed counter? For one thing, the advantage software has over hardware, software is very easy to manipulate. Hardware, once you got it, you got it. So I could do most of these programs that you're doing, I could do with relay logic. Right? You understand that? And that's basically what we're doing. But that's hardware. If I wanted to make a change and it's hardware, what would you have to do? You have to rewire it, right? You understand? If I want to make a change with a program, all I have to do is what? Go ahead and change it. So what advantage does hardware have over software? What's the main advantage? Software is slow. So every time I have a timer, what I do is we don't see it, but we insert a subroutine into our program that is a program that handles a timer. That sucker might be 2,000 lines long just to handle the water, a timer. I come up here and pop it in there. It adds 2,000 lines of code to my machine code program. Software is slow, guys. Hardware is fast. So the advantage of hardware over software is that hardware, a hardware counter would be a lot faster than a software counter. So the problem we have now, guys, is we've got encoders that we put on the back of motors to sense the speed. We got DC motors running at 7,200 RPM, revolutions per minute. You got an encoder that's got 100 marks on it. Think about how fast those marks are flying past that. There ain't no way in the world a software counter would keep over that. So one of the things you look at and say, okay, how fast can a software counter go up to? So what they're starting to do, since we're dealing with a lot of these encoders on these motors, is they're actually putting counters in the PLC, hardware counters in the PLC. And these are called what? High-speed counters. So if you're going to run an encoder which senses the speed of a motor, then you're going to have a PLC that's got at least one high-speed counter in it. So you don't have a program instruction for a high-speed counter. You got instructions to configure the high-speed counter, right? And also to get the information from the high-speed counter. So I can go back and scan it every once in a while for me, that's fine, but the counter won't miss any counts, right? You understand? I might, if I'm looking at RPM, I might go out and read it every second, right? You understand? But that thing encoder's flying by in microseconds, right? You understand that? So all we've got to do with high-speed counters is there's no high-speed instruction count. There's no high-speed counter instruction, right? We have instructions that allow us to do what? Set it up, right? How to configure it. That's all we got. And then how to access it. How do you access the accumulator on a high-speed counter? That makes sense? So here's our high-speed counter instructions. Trig instructions, sine, cosine, tangent, arc, sine, arc. And so this is not supported by the 1100 PLC, so they're what? Grayed out, yeah. Advanced max, absolute value, swap, DCD. I'm waiting for it to pop up. So these are encoders, one 1/16 to 4, and this would be a 4 to 1 of 16. We might show you all those. Where's all our they stick these things somewhere. So here's our copy, here's our field, right? And data log, and we're not going to look at that. PID, we might talk a little bit about that. Pulse train output, this just outputs just a bunch of pulses. Pulse width modulation, this is what we use to control DC motors now. And this is a user interrupt disable, so this is where you can actually disable the interrupts. So here's our move instruction. There's move. And then this is move with mask. Are we okay? And I'd have to find the stack instructions. So here's FFL, so that's first in, first out load. First in, first out, first in, first out download. But I don't know where those would be up in here. They're in here somewhere. Everything that's grayed out, what does that mean? It's not supported by this PLC. It could be supported by another MicroLogic PLC. Are we okay? And what you're going to find out on new PLCs, there's none of this garbage over there. You control the memory. They don't dedicate any memory to any data files. So this is what wait a second, let me get back there. So when I go in and look at my registers inside my microprocessor, as I get back to it, so here's what we got. We have these are actually registers in the processor. We got what mode it's in, the CPU, first pass. So there's your first pass. So that would be 15. The pre-running clock. So we can use the pre-running clock for timing instead of trying to use timers. Scan time math. What I'm looking for is I'm looking for the index register. And I don't see it. I might have to look up the other PLC. Guys, I don't see the index register. This was where it would normally be at in where? Yeah, the controller properties. No, I'm sorry. The actual processor, right? The processor right here. You know, that's where we configure the STI. The STI is not an instruction either. We configure that. So the way we specify index addressing is we start off and we put a hashtag. So a hashtag specifies index addressing. So here's our move instructions. So what can we do? So we got a source. This could either be immediate addressing or it could be any of our other addressing modes. Your destination cannot be immediate addressing, right? So this is the immediate addressing. So here's the actual number, but where could the information come from? So yeah, so it could come from. So what I'm gonna do is I'm gonna come up here and I'm gonna turn on my O simulator, and then I'm gonna come up here and I'm gonna come up here. This could come from a counter accumulator, so I could come from like C5. So anything I can address, guys, I could put this. I could take the accumulator, and then I could do I could move it somewhere. I could take the accumulator of a timer and move it somewhere. I could take the contents of a memory address and move it into another memory address. I could take the contents of an input. So this is 2.1. I'm sorry, 2.0. I don't know if I got. Let's see if it requires the dot. Yeah, it does. And then I can take this and put it somewhere. The destination has to be a what? It's got to be a data file. We could put it into a timer. So there's our timer down there. So I could go here. I could say what T4 colon 0 dot, and I could put it in the preset register, right? Okay. So where's this information coming from? Well, the input port, no, 2 is that output. I need to bring it to 1. Sorry. Okay. So what that means is now what I'm going to do is we come up here and if we download this and then we go to run, then whatever I come over here and bring into my input. So that's one of my. Let me set up the other one first because I'm bringing in that bit right there. And then we come over here and close the switch right here. Then whatever is there does what? But this is binary. it converts it over what for us? It converts it over to decimal. So I can come over here now, as if I come over here and change these inputs, and my number should be changing, right?
So can you actually use that as another way, like, as you can see, it's showing your destination down there, it's 25752, like you got it twice, because you got 2403, or whatever, twice.
Well, this is my destination. This, understand.
Yeah, I know, but you got like the N70 right there. Could you make that like a different
Oh yeah.
input area and then like add them together into that destination? They both go. You see what I'm saying?
No.
Well, he ain't got them turn on. He ain't got a switch for her turn on.
Yeah, but what?
This one won't do any. This is going to take whatever's in N7.0, which we have no idea where it's at, right?
Put it into the same destination.
Yeah, well, this would probably give us a problem.
Oh.
Right
Would
now,
it
because
add them together, or would it just like freak
no, they'll just freak out. In fact, if we did this in if we did this in 500, we would have probably got an error on the run, because I'm getting two different sources for the same location, especially if we keep them enabled at the same time.
Yeah, I was wondering if it would just add them.
Yeah, see what happened? It just messed it up.
He counted it up.
So no, you wouldn't do that. So I see what you're saying now. So we could, but what we could do is I could bring in this input port. I could bring in that input port. I could compare them, right, to see if they're the same. So when we specify this destination, this is direct addressing, by the way. It can be any of those files over there that we can get to, right? You understand that? So you can bring input information from an input port, right? So I could take it from this input port right here, and I could send it to that output port. So what we'll do here is let's go offline, and then so I could send it to output, right? Output : let me get my thing out of the way so I can see my space. Output : and that's 4. Let's send it to 2 because I've got it at 2.0, right? And then we'll download it. Of course, what it's going to look like, see that? So we can input information directly from an input and send it to an output for some reason if we want to do it that way. Make sense? Yes or no? So what do we do? What can you do? What can your source be? Could be any input port. Could be an output port. So I could take that, because you got to remember your outputs are, we're actually updating a data file, right? And then what the computer does is it comes over here and looks that up for you. So, I could come down here and I could read an output data file. So I could take output : 2.0, which is the one I'm dealing with. And here they're going to send it into the preset. So now when I come through and close that switch right there, oh, sorry. So what I did is I read this input port, I read this output data file, right? You understand? Y'all understand outputs are a data file, right? And then we set ones and zeros inside a data file, and then what happens is our what? It just masks this, right?
Do like output 2/0, 2/1, and then only light up one of them.
What's that?
Where it says the destination, can you go down to like bit level? You only go to the word.
No, not with the move instruction. Your add instructions and your move instructions deal with bytes. Now we can strip off sections of it by using what we call a move with mask, which means it strips off what we don't want, and we'll look at that in a second.
So why did you turn on switch 6, 7, 11, 13, 14?
I just was making up some.
It was just using
What I was showing you is I could take an input port. So instead of using this input port, since it's controlling the whole thing, let's use this input port 3. So let's go offline and let's go to input port 3 dot, and then dot means I'm going to get the whole word, right? Dot 0. Okay. So now what we're doing is we're using this input port over here instead of the other one. Okay. So what we're doing here is whatever I come up here and flip this switch, so that should go to 1, right? This should be 2. This should be 4. This should be 8. This should be 16. This should be what, 17, right? Understand? So what I'm doing is I'm reading this input port. Now it's not displaying it in binary, it's displaying it as its decimal equivalent. So if you came over here and took this whole thing right here, all the ones I have closed, and wrote 1 down, and all the ones I have open, you wrote down zeros and converted it over, it would come up and give you what? 26,897. So what I'm doing is I'm reading this input port. My application is converting it and displaying it in decimal, right? You understand? Okay. And then here I'm reading the output port and sending it to the preset register on timer, which is not on there. That makes sense? So what I'm trying to say is the source can be what? Anything. Of course, I wouldn't send I couldn't send it to an input port data file because it would be reestablished by the next time it scans, and it would go back to whatever the input port says. But I can definitely send this to an output port.
Like say if you turn off input 1 and all the outputs go off.
You would have to do that. You could use a single input, but you'd use a contact, and you would probably use a field, or you could use a move. Yeah, I could. I mean, you're right. I could take this offline, and this is what I was doing in the other program. This is the instruction I was using right here because I wanted it to turn on certain outputs. So this is the instruction I used. I used the move instruction. But instead of using a switch, I use that first scan. I don't know if Logic Pro supports first scan or not. I don't know if it supports that instruction. Okay? Makes sense? No, this is not index. This is just direct address. We ain't got to the index register yet. So what they did is they talked about index address, and then they jump into just standard moves, and then we'll get into index address in here in a minute. But this, I don't know if, I'm sure Logic Pro supports it because, they're very popular, very, very. So this is just a bunch of move instructions. So what's this getting information from? So here they're taking an N7 file, they're putting it into this B3 file. Here they're taking, here they're taking this and moving this into the accumulator, right?
That's supposed to be the thing.
Yeah, I don't have a plus idea what this is. Is that the way it is now, Texas?
Yeah. It says that right there is the thing to show an index.
No, that's not what an index is.
Yeah.
No, this is not index address. Bit S24 is used as an index pointer to point to the words in the data file. Oh yeah, I'm sorry. This is right there. I didn't see that. Is this right here? The hashtag. So what that means, this is using what we call index address. So what it does is it takes the contents of the index register, which is what? What do you think whatever we put it into it. Normally by default it sets it this, right? That makes sense? And then this right here would be what we call our offset. So what offset are they using right here? 0. So what it's going to do is going to add this to that, and then of course this is going to put it, it should put it at N70. So I don't know what they're doing this for. But if I came over here and put like a 32, and my index register had a 63 in it, then what would be the address we'd be dealing with? What? Yeah, 95. Yeah. But what we can do with the index register, guys, which is really, really clear, and we'll look at this, is it can automatically control this. We wouldn't necessarily use index addressing for something like this, but we would definitely use it for other features. So the bit shift that we was looking at, bit shift left and bit shift right, this used index addressing. Because what would happen is once it shifted over an entire word, so I could set up a 64-bit shift. Well, what it would do is it would increment the index register, and once it came up and did 16 bits, it would automatically do what? Go to the next address, go to the next address, go to the next address, and go to the next address. And it did this automatically by incrementing the index register each time through. So what that meant, I would start off with this, and then we would do a bit shift left, and then it would go through 16 bits, and then it would automatically increment the index register. So it automatically moved to what? To word 1. And then when you went through those 16 bits, it would automatically increment and it would automatically go to these words. So normally we use index addressing for things we want the processor to automatically increment through. And we normally leave the index register alone, because normally we start off with an offset we start off with 0, right? Does that make sense? So this is the way we indicate index addressing. We come up here and start off our what with a what? A hashtag.
What's the S24?
That's the index register. S24 is the index register.
Okay, so then
that's where we would load S24. The 1100 don't give you the ability to change the index register, so you start with 0. But I think the SLC 504 gives you the ability to change, put whatever you want in the index register. This guy right here, I'd have to look and see. We'd have to look and see what's available. But
so you can reset it according to the S24 reset?
Yeah. Yeah, this would reset it. This would always reset it back to what? 0. So this is not supposed to be a 5. This is supposed to be a what? S. Yeah. Y'all's a 5 or y'all's an S? What? It's a, yeah.
The newer book is
It is in the new book? Okay, cool. So yeah, up here, that's definitely a what? A 5. That's what I couldn't understand. So S24, what they're doing is they're taking this and they're actually putting it in the index register. So what they're doing here is they're counting up. So we start off with 0, so we'll offset by 0. So we'll go to D3, 0. Then they do what? Then they increment the index register, right? You understand? And then we do what? Then we update the index register. And then the next time, the index register would have 1 in it. So where would it go to the next one? It would go to B3 plus 0 would be what? 1, right? You understand?
D3 1.
Yeah.
So that's the way it So it doesn't have any examples of where the B3 like it's nowhere else in the thing. B3.
Yeah, well, this is just a demonstration, and we probably got this. This program in RS Logic Pro.
I was just looking at right then. I was like, wait, so why?
So this is chapter 14, right? Figure 1. I think these figures are off. I think that's the one I had.
They have 2?
Well, I think they had, let's look at figure 2. Okay, so this is it. So what we would have to do here is all we'd have to do, and the problem is they're taking N7. So what we probably need to do is set up N7. And they're not putting anything in N7, are they? Oh, no, they have. So what they've done is they've automatically loaded what? Yeah, some values in it. 1, 2, 3, 1, 2, 4, and 8. They've automatically loaded values. So what's going to end up, if we run the program, as we go through, and we look at B3, it should do what? Should start off at 0, and then as we increment through this, it's working the way it's supposed to. So we don't need N7, so let's look at the B3 files. So right now it's got what in it? 1. Okay. Oh, it's already in there. Can y'all see it shifting through? So it automatically is doing what? Well, no, so this is 1. This is 2. So what we're doing is they're taking these groups right here in N7, and then they're putting it in here, right? You understand? Does that make sense? And then what they're doing is they're automatically incrementing S24 each time through the list. Yeah. So if we turn off the switch, then I should be able to clear these out. They should have an instruction where we clear these out. Okay. Yeah, 1 should reset it. Reset the counter, right? Then we should start off with it automatically incrementing through these addresses, right? That makes sense?
Once it counts up to 4, it'd be an 8. Reset it because it says C5.
Okay, yeah, should do that. I didn't see. Yeah. So there's the 1, right? And then what did it do? It automatically oh, I know what's going on. Yeah, I'm sorry.
You had to reset it on.
Well, I had the reset on, yeah.
Oh, reset itself.
Yeah, I had the reset on. Sorry, guys. So this should work. So let's change these over to push buttons anyway. So if this works, then we should take whatever's in N7 with an offset of 0, right? And right now my N4 register, since my S24 is cleared out, now it looks like it is an S. So in fact it bounced on me. It looks like 1, 2, 3, 4, right? Now if I hit it again, it should do what? Yeah, it should reset. And then, of course, it shouldn't do anything after that because it's just repeating the same thing because the N7's not changing. So what we're doing with this one is we're just kind of demonstrating index addressing. So here we start off with clearing the index registry, which is S24, right? Understand that. And then we come up here in N7, we're offsetting by what? We're offsetting by 0. So this is your offset. What we do is we take the contents of this and then we add it to whatever's here, and that would give us our address. Right? So we're saying D3, and we start off with what? 0. And we take what, well, we're taking what's in 0, putting it in bit 0. And the next time through, we're taking what's in bit 1 and putting it in bit 1. And we're taking what's in bit 2 and putting it in bit 2. And what's in bit 3 and putting it in bit 4. And they're just demonstrating how we can use index address. Now here we're controlling the index register ourselves, right? You understand? The bit shift left instruction, that instruction controls the index register for you. So if you tell it to do a 64-bit shift left, once it goes through 16 bits, how does it know to go to the next word? Well, it just increments the index register. It automatically goes to the next word for you, right? You understand what I'm saying? So the bit shift left uses index address. And the bit shift right also uses the index address. But it automatically increments the index register to automatically move on to the next address. And then we've got other instructions too, guys, where we come in and use this automatically too. Mask, because this is mask with move, and we talked about this. So move with mask, this allows us to strip off. So we looked at AND. Everybody understand what an AND does? What is it? What do we do with an AND mask?
Has to have 2 words and 2 truths to make a
true output, right? But a 0 and a 1 or a 1 and a 0. Yeah. So what I would do is if I come over here and I've got a bunch of bits, and let's just use 8 bits, and I want to let this guy right here come through, and I want to mask off all the rest of them. Then I would come down here, and this would be my mask. So what would happen if this bit was this would be a what? 0, 0, 0, 0, 0. That right there would be whatever that bit happened to be, and then this would always be a 0, and this would be a. So what we do with an AND mask is we strip off bits that we don't want to come through. We mask them off. So with an AND mask, we make sure certain bits are cleared. With an OR mask, we make sure certain things are set, right? So this move with mask, this is an AND mask. So if I was to come over here and I was interested in, I was reading an input port, right? You understand? I was reading one of my input ports. I don't want to use this. I want to get back to Logic Pro. And here you can, on our Logic Pro, you can select any PLC you want to, and it still gives you the same I/O configuration. So let's say I came in here and I'm going to use a move and mask, and this don't have the instruction palette. Oops. Move, right? Move and mask. So my source, what do we want to do? So I'd come over here and I would say input 2.0. What bits do we want to come through? Well, let's just for sake, I'm gonna come up here and I'm gonna put 00FF and I'm gonna put hex. That means okay. So what I'm doing is I'm stripping off everything above bit 7. And then my destination, we'll put it somewhere where we can see it. So let's put it in B3. Okay. So then I got to assign this to input. Everybody okay so far? So this is a move with mask. Get rid of that one, even though, and then we'll download it. So what I'm doing is I'm making sure that these bits right here are always what? Set or cleared. So if I AND anything with a 0, I don't care what they are, what's my answer going to be? 0. Okay. So what I'm doing is I'm stripping off these upper 8 bits. I'm not stripping it out of the input register. So the input register is a data file. So I'm going to take whatever's coming in from this guy right here, and I'm going to strip it off before I send it out. Let's instead of sending it to a B3 file, let me go back off so we can actually visually see this. Let's send it out to one of our outputs. Okay, so go down this. So what we can do is we can see this work instantly.
So you said we had an X and converted over to decimal street? Is that what happened?
Yeah, it's bad about that. Yeah, 255. Did it? I entered in hex. Alan Bradley's got a RSLogic 500. Is we can enter it in different bases, but as soon as it does it, it's going to do it in decimal. So if you want to keep up with these, you need to write them down. What you notice when they get up here to the new form where we say 16 hashtag, then we come up here and enter a hex number, then it's always going to be in what? It's going to be in hex for you. So, which I like better. So this gives you a heartache because if I was to come up with a real complicated mask, I would probably need to write it down because either that or I'm going to have to convert it over to what? To decimal, right? Or I can send it to a port. So what this, what we did here is I've downloaded this, and I'm going to take whatever's on this input port and just put a bunch of switches in. I'm going to close a bunch of switches. And then I've got some closed up here. And then when I come up here and I activate this, what? Yeah, I did. I thought I did. Maybe not. Oh, y'all see what I did. This guy don't give us errors. Yeah, and I left off the 0 there. So you can do things in RSLogic that don't work. And I messed up again too. Let's see what I did. Yeah, I used an output port that didn't have anything in it. So here's all these guys. Bit 15 was set, but it came up cleared, right? Bit 14 was set, it came up cleared. Bit 13 was set, it came up cleared. When I got down below here, this is 1. It's true. This went true. This is true. This went true. This is 0. This went 0. Y'all see what I'm saying? So what did it do? What did it do? What did the move with mask do? It stripped off whatever bits I wanted to see, right? You understand? So I can use this mask, but so this is what I do with an AND operation. The AND operation is a mask operation, but this you do 2 things with 1 instruction. So are you okay with a move with mask? Yes, no?
The only thing different between an actual move and a move with mask is the move with mask actually script.
It's an and mask too. You can't do an or mask here. If you do an or instruction, so we use ors to make sure certain bits in our answers are set, right? We use an and to make sure certain bits in our answer is always cleared. Move with mask is always just an and mask. So you got three things, you got two things you got to specify. And one of the things you got to specify. You got to specify where your information, where's your binary information coming from, is your source, right? What your mask is, and then where you want to put your answer at after the mask. And the mask is going to always be, as far as I know, the mask is going to have to be immediate address. We okay?
Did the mask has to be immediate?
As far as I know. We could try that and see if it would work. Let's see if the Logic Pro will let us do that. It looks like it can be direct addressing too. So let's see if this works. What I'm gonna do is go out and do N7 0, and let's put something in there. Let's do it different. Let's use the same mask so we don't get us confused. So let's go to N7, N7, and let's put the same mask, which would be what? 255, and we'll see if it does the same thing. Huh? No, I didn't change the program. All I changed the contents of the register. I wouldn't think I would. I wouldn't think I'd have to download it. So you have access to your registers that you can change it at any time, right? Yeah. So it looks like it worked. So you can get your mask from another addressing mode, immediate addressing, or you can get it from a register or the other addressing mode. It could be indirect. You texting back there? Miss Boykin, what are you doing back there? Are you paying attention to me or are you texting back there on your phone? Huh? Okay. This was the example. We've already went through this. Using the mask move instruction reads data from input port 2, runs it through a mask. They're basically using the opposite mask of what I'm using, right? By the way, the 16-bit number, it interprets it as a negative number because we talked about when we use signed numbers, the most significant bit is your sign bit. If it's set to a 1, it means it's what? Negative. So they interpret this as a minus 256. But it don't hurt anything. It's still going to use this mask. It's just that when it converts it to decimal, it's going to use it. It's going to interpret it as a negative number. You understand that? First in, first out. First in, first out, last in, first out. These are our stack instructions. So what do you think? So what we have the ability to do, or what we need the ability to do, is be able to store information for temporary use and then bring it off without me having to constantly specify addresses. So what we have is we have something out there that we call a stack. We have one called first in, first out, and we have one called last in, first out. What do you think that means? So I'm going to come over here and I'm going to store data on a stack, and it's going to come over here and put the data in a stack, and it's going to put it at an address. Then I come up here and I save something else on the stack. Where's it going to go? Well, it's going to probably go up here, right? You understand? Then I come over here and I put it on here. I stack it on right there. And then I come up here, I put on another one, and I stack it right there. And we call these pushing. We call it pushing the stack, pushing data. Now, we can do it two different ways. We can get first in, first out, or we can use last in, first out. So what that means is when I pull information off the stack, if it's a first in, first out, what does that mean? It would pull it here, and that would be the first one we pull off the stack. And then the stack pointer would automatically decrement, and the next time I pull, it would. So what happens is when I'm pushing the information on there, we call it pushing. Taking it off, we call it pulling or popping. They call it popping the stack. So what happens is I start off with my stack pointer set at a certain address, and what I do is I tell it to load the stack, a first in, first out stack. And what it'll do is it'll put that first information on a first in, first out. It'll put it where? It'll put it here. Then I come up here and I load it again, and it'll automatically do what? It'll automatically go to the next address. And I load it again, it'll automatically go to the next address, right? You understand? Then I load it again, and what would it do? It automatically goes to the next address. Now, if I'm using a last in, first out, when I pull it, right, when I unload it, so it's called an unload instruction, then where would it get it from? It'd get it from the top of the stack. And then the stack pointer would automatically go to the next address. And then if I pull it again, it would pull it from this address. And then the stack pointer would automatically decrement, right? It would automatically decrement, and it would take me to the next address. So when we put information on the stack, we got two options. Go ahead, Mr.
That's what I was asking. Is it the same putting information in it starts at the bottom, then to the top, but withdrawal.
Well, if you use what we call the pop the stack, it either comes off the top of the stack or the bottom of the stack. And you don't have to specify an address. All you just say first in, you say last in, first out, unload, and it'll go to the one where at the bottom. And then if you use it again, it'll automatically go to the next one. Now you're not wiping that data out. All you're doing is moving it. If you knew these addresses, you could go out there and get them yourself. But what it does is gives you the ability to go out and temporarily store data and then do what? And retrieve it in the same order you put it on there. That makes sense? Or in the reverse order. It depends on how you use these instructions. Concept of storing and retrieving pallets is similar to the way data is placed and retrieved from a stack. A group of consecutive data words, they said registers, but I changed it to words, and then placed temporarily in a memory location or a buffer. A buffer is just a go-between. So here's our two types. I went backwards. Okay. This would be like we're talking about. Setting up a buffer storage area and then trying to keep up with stuff. So here we come over here and they're saying, okay, I'm gonna come over here and something's going on over here, but this guy over here is still running. So what we'll do is we'll just go up there and do what? Just stack them up, right? And then when we take them off, it would be what? So you go into a lot of restaurants and they'll have plates out there. And what type of stack would that be? So you go down here at
The last one they put on, the first one on.
Yeah, it'd be the last one they put on would be the first one they put off. A lot of them had those spring-loaded things that worked on gravity, and the only one you could get to was the what? The top. Of course, you
Last in, first out.
last in, first out. So the plates are last in, first out stacks.
I'll go to that one.
Very easy to do, right? When you can go down here, they bring them plates out and they'll stack them up, and the last one on the top, that would be the first one you put. When stacking data, stacks grow larger as data is stored on the stack. By the way, technically, when we put that on the stack, they call that a push. The instruction, but if you ever hear say, well, you need to push it on the stack, that's what they're talking about. And then when we take it off the stack, they technically refer to it as a pull, or they'll call it pop. Pop the stack. You need to pop the stack, which means do what? Pull the information off. But the instructions that we got, and as the stack grows smaller, the data registers are retrieved from the stack. You're not wiping the data out, you're just incrementing through it, right? So if you knew where the stack was, you can access that data just by using your other address in there. So here's the first in, first out, last in, first out. So here's our stack, right? Let's see if this takes in. So they're calling it what? Pop stack. So what's the top one? I don't see this. So here's the first in, first out. Here's the last in, first out. So what we're doing is we're saving information on the stack. We start off with what? A. Then what? B, D, D. And then we pop the stack. This is a last in, a first out. D is the one that came off. Right? They're showing the stack moving up, but the stack don't move up. The stack just stays where it's at, right? You understand? It's just that you copy the information from that bottom of the stack and put it somewhere. You're not wiping the data out, it's still out there. The only way you would wipe the data out is if you place something else on the stack. So if you push to the stack, then A would move down to here and wipe what was originally there, right? You understand? That makes sense? So the stack itself is not moving. It's my illustration would be more correct. So it's not bringing D out, it's just reading D and bringing it out, and then the stack pointer automatically goes to what? C.
It stays in the same spot, it don't go up.
No, the stack don't move, right? So this is the way it works. And then, now, this would be the top of the stack. This data is still there, but this would be what we call the top of the stack. The contents of D is still there. It's going to be there until you override it, right? You understand? And then what would happen if I pop the stack again, then my stack pointer would automatically go to that address right there. And now this would be considered the top of the stack. The top of the stack is where data is going to be placed at the next time you push information on it. That makes sense?
So the next time you put your information on there, it'll overwrite.
Yeah. And if it pushes down, it won't overwrite A, but it would overwrite what was in C.
Gotcha.
And if you push something else, it would overwrite what was in what was in D. But what we do is we can push information on and pull information off with just two instructions, right? You understand? Instead of me specifying an address, I load my stack pointer with where I want it to be at to start off with, and then from then on, I'll leave it alone, and it takes care of itself. It's just that I have to know the order that I put information on there and the information I take it off. The stack is used automatically, guys, when you use a jump subroutine. Because when you use a jump subroutine, when it ends the subroutine, it has to have the ability to come back from exactly where it left off. But what does it do? Well, when you use a jump subroutine, it saves where it's at on the stack. And then when it sees the return instruction, what does it do? It automatically goes out and pulls that information out and puts it right back where it's supposed to go. So we use it with the JSR. It's just that it's transparent to us. Are we okay? Y'all guys go ahead and take another 2-minute break. LFL, what do you think that would be? Last in, first out, load. This is what we use to put information on the stack. Then LLU would be last in, first out, unload. So that would be what we use to get information off the stack. hopefully this works. I just did this while y'all was on break. So we'll do this real simple. So I'm bringing stuff in from input 3, and then I'm putting it on stack. I set my stack length as 10. We're using R6 as our control register, so that'll tell us if we overflow our length and stuff like that. So if I go to 6, if I go to 11, we should get an error saying we've exceeded the size of our stack, right? And of course, if we exceed the size of our stack, that could be causing problems because we could be using our memory for something else and we just overrode it. So what I've done is I've set up a stack. My stack register set at 0. Then we're going to take whatever comes off input, and we're going to store it in N7 with an offset of 0 using what addressing? Indexed addressing, right? So let's see if this works. So I'm gonna come over here and just put so I'll just put let's just put 0, 1, 2, 3 like that, and push it on the stack to make it real easy. So I'm gonna push it on the stack. Oh, I'm not in run. Make sure I download it. Can't see. Let's switch it to run. Oh, I did that wrong too. Keep getting PLCs messed up in my mind. So that's not resetting the position, but we'll see. So we'll come up here. So we'll change our contents, push something else on the stack, change it, push something else, change it, put something else, change it, put something else. And all I'm doing is just, okay, and then we're done, right? And then what should I do now?
Unload.
So we're going to unload it, but I'm sending it to,
Send it back to the same spot. R6.
no, that ain't what I want to do. So let's see if they'll let me change that without screwing it up. And we're not, let's see if it lets us get by with it. Let me get by with that. Yeah, thank you. So it's not working. So we're loading it on, we're so this is where we're getting it from. So this example, they're getting, yeah, that's the problem. Yeah, so let's see. So this should be the same right here. So this is where our stack's at, right? So this is where the stack's at. So it's going to be at, so that was right. N7:0. Okay, where we want to put it at, let's put this at, we'll put this at output port, 2.0, right? So let's see if this works. So we'll load the stack. So I'll start off with 1, and I'll turn this one, turn on this one, turn on this one. Should have made it shorter, shouldn't I? Of course, I could be able to stop at any time and do what? And then unload it. Last in. So what did I put on there last? Let's see what it's showing. And somehow I lost that bit. So what we did is I set up a stack with a length what? 10, right? Last in, first out. So the last thing I put in there was whatever I stopped at. Huh? Yeah, but I was just closing all these loops. And then of course when I pulled them off or popped the stack, it just pulled it right back off, right? I see that. But this was last in, first out, right?
So when you unload them, where did it go? What destination did it go to?
I'm sending it to the south. Okay. So we can literally see me pulling the data off and seeing it. So this is what we like. So source, this is where our information is coming from. Where am I getting my source from? Input 3. That's the way I can change it really easy, so you can actually put different data. This is where I'm putting it at. So this is this is your top of your stack. This is where you start off with, right? Everything. Okay. I'm putting it in 7, but I'm having to use what address in mode? Index, right? So it automatically is incrementing the index register for us every time, right? Y'all understand that? Huh? And then control, this is where it keeps up with our status, what's going on. So if we look and see what's in R60, so here's our bits that we would be using, right? So EM, where's the EM bit right there? So it's what? It's set, right? The done bit, it would be set. So this is basically the status register, but this is not the status register that's in the microprocessor. This is the status register that we set up for these other instructions. Are you okay? So you would have to specify one of your R6 registers. So your shift left, your bit shift instructions, those use the R6 register, and this right here also uses the R6 register. Or data file, I'm sorry. So there we go. Y'all see that? Pretty neat, right? So what we could do is we have a place now where we could just store this information. We can store a bunch of information, right? And then do what? And then pull it off in the same order we put it in, either reverse order or in the same order we put it on stack. And this is called the stack. We have 2. We got last in, first out, and then we got first in, last out, right? And of course the instruction LFU. So this is what we use to pop the stack, and that's what we use to load the stack. Any questions on this? And every one of them I've ever seen, when microprocessors first came out, that stack was something they came up with, so we could use these dumps over things.
So they got the last in, first out, no, first in, first out.
Yeah. LF, last in, first out, then the other one would be what?
First in, first out.
Yeah, so it would be.
Oh, so you need to work both ways. Okay.
But the first in, first out, we would pull it off the bottom, right? And the last in, first out, we'd pull the first in, first out, we'd pull it off the top of the stack. The last in, first out, we'd pull it off the bottom of the stack. I said that backwards. The last in, first out, we would pull it off the top of the stack. And then the first in, first out, we'd pull it off the bottom. I got it right that time. I get it right?
You got it right.
These other ones, these are pretty simple. We have copy. So what we do with copy, guys, is we copy you say, well, what's the difference between a copy and a move? Got to be a difference, because the move instruction is not actually a move. So if you're in Windows and you move a file from here to there, it deletes it over here and moves it over there, right? So the move instruction is basically not nomenclature, right? It's actually a copy. But now we got this command called copy. What does this guy do? This copies a bank of stuff. So we can take 15 bytes over here, or words over here, and copy them where? Over to another place. So this guy is going to also use index addressing. Yeah, copy and paste. So this guy right here does what? Can use instruction to manually enter the file with a file with constant numbers or data from another file. Down handling instructions used to block data. Let's see if RS Logic supports this. So we'll come over here and let's get rid of this. In fact, let's just go to new. I don't know why I didn't need all those instructions. So where would this guy be at? We're in the what? Move. Logic. Oh, let's just, this guy here don't have the instruction palette, so it would be hard to find. First in, first out. File and miscellaneous. We might have to do this with a real PLC, guys. Huh?
Look like you skipped the program file.
So bit, timer counters, output, compare, we know it's not in there, computer math, move, program control.
It was just one I saw. You went past it.
It's not in file either. In fact, the file is what? It's blank for RS Logic, for Logic Pro. In I might have to bring my other PLC. We'll just see if it supports it over here. So B, right? Okay. So let's see. This is actual RS Logic 500. So there they are, copy and fill. Yeah, and that's the one that was blank under Logic Pro. I'll have to look at the PLC. I don't know if it's available. I'd have to find it in this one too. This guy's got a ton of instructions available to it. So you can see that the setup of this, right? So we got what? We got a what? source,
and
destination,
how long?
and how many you want to move, right? Y'all understand this? So we could come over here and take, use an indexed address, and we could take B3:0, and then we could come over here and send it out to N7:0. And we could specify a length of what? 10 bytes. Huh? No, 10 words. 10 words. Yeah, it's 10 words. Dev table 4. Oh, thank you. Says it already exists. So I was trying to assign it a different number. So it clears up. So what we would do, I don't have the PLC hooked up, and so what would this do?
It will copy what's in B3 and put it in
B30, B31, B32, B33, B34, B35, B36, B37, B38, B39, all the way to 9, because we're starting with 0.
You're right.
And copy it over to N7, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what we have here is with this guy, is we could copy a block of data from one data group of data files and do what? Put them somewhere else.
But it'll also stay in B3, 0 to 9.
We're not wiping them out, we're just copying.
Gotcha.
So this is a true command, we're copying. Now it would wipe out whatever's here, because we're writing, right?
Yeah.
Reading information from memory don't hurt it, right? But writing does. Okay, does that make sense? So yeah, we would lose whatever was here. So N7, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, those would be replaced or overwritten with whatever we can from it. So the copy is what we come in and we do what? We can copy a group of data files from over here and do what? Put them somewhere else. It makes sense. You okay? I mean, we can do this, but I don't have the PLC hooked up, but this is pretty straightforward.
Now,
So what the sources where you're coming from, you gotta use what address, you gotta use index addressing, so it can automatically do what? You can automatically increment the index register every time it moves through the data file, right? You understand? And then this is where you wanna do what? Where you wanna put it, and this is how many you wanna copy.
It had to be indirect too? You just had to be indexed too?
Yeah, because it's gotta automatically increment. In fact, I didn't do it, it would probably automatically put that in there. Let's see. So let's see if I come up here and just try to put B3:0. See what it did? Yeah, it automatically changed the index address, and so it's required. You don't have to put it in there. It's just required because index addressing allows us to automatically go through tables, right? Y'all understand that? That makes sense?
So the destination has to be.
Yes, because it decrement. So what it's doing is it's pointing at it's using the same offset, right? You understand? Yes or no?
Copying everything. Yeah.
Okay? Okay. So what would you think the next instruction would do? Fill. So my source is not going to change. So if I came over here and put AAAA hex, okay, so I can use immediate address in here. And then destination, then I come over here and put B3:0. It automatically changes it over to what address mode? index addressing, and then I would come over here and put 10. So what would this instruction do? It's going to take 1 0. It's going to take 1 0 1 0 1 0 1 0 1 0 1 0, and it's going to fill 10 bytes of memory with that one word. So this up here is not here the source does not have to be index address. It could be direct address and indirect address, or it could be immediate address. Your destination is what has to be indexed addressing. So what we're doing now is we're filling a group of memories, right? You understand that? One place they wanted to do this, if I come over here and let's see if I can find this. So these are the PLC programs that's actually running the Festo line over there. So this is the first line. We call it the distribution station. And you can see this is written the way big programs are written. They start off by doing what? Up to something in file 4. Of course, what they've done is they've renamed ladder 2 to program underscore OR, but it still has ladder 2 over there. So how do y'all rename these? You just right click and just change the name, all right? Okay. To see these other subroutines, what I'd have to do is I'll just come down through here and open up the tabs. Okay. So this is what we do. So we set up a main subroutine. It knows just about everything here does a what? JSR, see that? And then that gives us the ability to set up another to take a big program and do what? Split it up, right? You understand that? No, that's not the one I wanted to see. Yeah. So what they're doing is they're taking the source here would be what? 0. And they're sending this to B3 0, 1 and 2, and they're just putting what out there? They're just putting 0. So when I reset this thing, when I hit reset, it goes out, clears out those bit files.
It makes sense now. So what we done did B3,
we didn't have the field because
we used the move.
We used the move because the bit files we would have to set up an array.
It makes sense.
And what it does is these bit files are used in the auto program right here to go out and set. So see, here's all the bit files right here. So instead of me going back here and unlatching all these things, right, and try to do a ladder program, what did they do? They just set them all zeros with one whack. Okay. So here they're filling up the output port. So they're taking output. Here I don't know why they use the full field because they're only going to do what? One link. They could have used a move. So they could have used the move instruction to move zeros into this location. So they're clearing out all the bit files. They're clearing out the output. So all the outputs go to 0, and then they return. So here this makes sense. Like I said, in the PLC3, it has a fill instruction, but we couldn't quite figure out how to use it. So what we did is we just used 3 move instructions, and it worked exactly the same. This looks familiar too. So what they're doing is they're setting up some blinking light, and they're just flipping these things back and forth. This is one of the things we looked at in PLC and PLC1, how you can set up a blink, right? You understand that? Well, another way to do it, if you're not really concerned with time, is to is to come in here and use your,
Clock.
yeah, use this guy right here. Oops, sorry. This free running clock right here. So the further you go up the line, the more of a delay you get. Let's bring up Logic Pro and show y'all what I'm talking about. Logic Pro does support this, by the way. So what file is this? This is S4, and then I choose a bit depending on how fast I want it to blink. S4 changes, because it depends on the processor. So I want to set up a blinking light. Well, what I could do right here is I could say use S:4/bit. How many bits? We got 16 bits to work with. Let's say bit 10. And delete that bridge. And then we'll come up here and just put one of our output bits, and we'll just make it flash. Output :2. Oh, I'm using a real slow bit. I was thinking something's not working. So let's use a faster bit. So let's drop back to 6. And so this would be a lot better to use than than trying to set up those stacked timers. You set here, you're set for what you got. Huh? Yeah, so this is really, all if I wanted to do was flash lights and stuff like that, and I didn't need 1 second or 2 seconds. So if we come over here and look at the processor status, it didn't show up. You see that thing is just over there just a running. And what you do is you choose a bit. The closer you get to 0 to us would look like it would stay on all the time. So odds are we're not going to use 0. We would just use what? Yeah, and this.
Keep it from flashing until you need it to flash.
Yeah, you could. Oh, I just wanted to show you what. Yeah. So you just put another input in there. So that's your S4 register. It's actually S2, but anytime you use S, it takes for granted the 2 is given. So then 4 is the free running clock, right? You understand that, and then you choose the bit. So we use this a lot because it would take 2 timers to do that flip flop thing that we learned in PLC 1. This is what you would probably use, but it's not as accurate. Your new PLCs are really accurate, and they'll give you like if you want a 1 second delay or half a second delay. So if you wanted it to blink on at 1 hertz, you'd use a half second delay because it'd be on a half a second and off. So yeah, you looked at that or the 5000. So this is that clock register we was talking about. So you can use it for a lot of things. It saves a lot of time. So the further you go up, the slower it runs, right? You understand that? So it depends on what you want to do with it. So copy and fill. So we use copy to do what? Take a block of data in one data file and copy its contents over into another. So we could do that if we needed to use it for something, or if we just needed to send this information off to some other world. Like if I wanted to transfer information from one place out to a display or something like that. We'll look at some of the ASCII capabilities that we have with these PLCs too. And also converting data from one side to the other, which we'll look at and we'll be further discussing. Data conversion. So the problem is when I get information from a input port, automatically it assumes that it converts it over to decimal, right? You understand that? The problem we have is that when we come over here and run these displays like this, so if I was to come over here and run this display, this is a 7-segment display, and it deals with numbers from 0 to 9. So if I was to come over here and take these switches over here and try to display them over here on my display, it's going to give me a problem, because even though it displays in decimal, everything is still in what? Binary. So if I was to come over here and take these input ports over here, if I can move these over, and let's say I take in these switches, so I'm going to flip these switches, and it's giving it to me in what? Binary. Well, it's actually BCD.
Oh, yeah.
So let's use these. So let's say I want to take these switches and I want to send them to that display. So we're going to take the switches, right? So how would I do that? Yeah, so I'm going to take the contents of these switches. So I'm going to get rid of this guy right here. And what type of instruction might be used? Convert a binary number in the source into a what? Into binary coded decimal. Right? It's going to turn binary into BCD. So right now, if I was to come over here and take these switches, so we'll just use a move instruction to start off with. I didn't want to download. Oops, not math, Rich, move. So we'll just take a move instruction. We're going to take the contents of these switches and put colon, let's take 3, and put 3/3.0, right? And then we're going to turn around and we're going to send it over here to this display, which is addressed at 6. So output colon 6.0. And then we'll download it. Okay, we'll switch to run. So this is a good display. So it's actually displaying this number over here in what?
Oh, that's
Hexadecimal. Now, who would understand that out there in the real world? Nobody. So what we'd like to do is we would like to display, we're going to have to reduce the number, by the way, because this guy won't do this number to big. So if we do BCD, the biggest thing we can go up to be would be 9,999, right? So what we're going to do, instead of just sending it over there, we're going to take the input and we're going to convert it. So let's go offline. Yeah, we're going to use a TOD instruction. So let's replace this push button. You're right. Thank you. And then where is the TOD instruction? That would be over here under Surely this supports LED.
Right down the street.
Where it is?
Right there.
Oh, there we go. So they got it in the computed math. So we're going to use input 1/1/0 to cause it to work, right? And then our source is going to be what? Yeah, input 3, right? And then our destination would be what? Output 6. Okay. So what we're going to we have to take off some of these switches off out here. Take off this big guy.
So the big ones on there wouldn't have been too big a number.
Yeah, it would have been too big a number. It would probably drop them, but we'll see. We'll see. We'll do that on purpose. So right now, if I took this number right here and converted it to decimal, what would that be? 1, 2, 4, 8, 16, 32, and 8 should be 42, right?
32 and 8.
No,
That was 8 and 16.
this is switch 5, so that's not, it's 1, 2, 4, 8, 16. I'm sorry, 8 and 16, what would that be? 24. Okay. So let's see if this is going to work. Magic, yeah. So what it's doing is it's taking this binary number over here for us and doing what? Displaying it in decimal format. So that's what happened when we overload this thing. Oh, I guess, no, it can do a 65, no, it can't do this. It's got to be dropping some things because we can't get to 65,536. So it looks like it's just dropping bits to me. So this is what's coming out. This is what's going to my display, right? You understand? But it's going in. Y'all see that? That makes sense? Everybody okay? So what's the other one? Well, these switches right here, these are called thumb wheel switches, by the way. This is what a person would input, like a motor speed or a count I want a counter to be. But what base is this in? It goes from 0 to 9, guys. So what's it giving me? This is BCD. But if I sent this to a counter, it would interpret this as what? Starts with a B. It would interpret it as binary, right? So if I was to come over here and yeah, we'll just change this back to a move instruction. So y'all can just see what's going on over here. So what I'm doing is someone will take input 5, and it don't make any difference where we put it at because it's going to give us the number anyway. Well, in fact, it's already given it to us. So I'm putting 9,999, and the move instruction is seeing is at what? 39,000. So I'm over here trying to load 9,999 into my counter, but my counter is going to be loaded with 39,321 because it's interpreting this right here as being what? Binary. Right? You understand? But what I want to do is I want to take BCD coming from my thermal switches, which is what these humans are dealing with. They don't understand binary. They understand what 9,999 is, but they have no idea what this would be in binary, right? So what are we going to use here? So here we're going to convert it from binary, from BCD to binary. BOFRD, where was that at? right here. So here's FRD. Okay. So what's my source going to be? From something to something. I don't know. You got me. So input, I'm going to take input 5. I'm going to take input 5, right? You understand that? And now I'm going to send this to my decimal display. So this is going to be output 6. Is that right? Okay, so we're taking the input, which is 5, and we're going to send it over here to the display. No, I don't want to do that because it just, well, we can see it go to binary, so that's okay. Yeah, because this guy does hexadecimal. So it came in as what? So let's take 270. I'll do it with my calculator, guys. So I'm gonna come over here and put my calculator into programmers. I'm gonna come over here and go hexadecimal 270F. I know it's an odd number, and then go to decimal on that, and it's 9,999. So what this does, it gives the ability for me in an outside world to deal with the decimal number system, even though my computer is dealing with binary, right? Y'all understand that? So I'm over here, I want a motor to run at 200 RPM. I put in 200, right? You understand? But bringing that into a PLC would mean nothing because the PLC is dealing with a binary world, right? You understand? So what I have is I have a method of taking binary and converting it to decimal so I can display and send information so I as a human understand it, right? Because I know the decimal number system. And it gives me the ability to bring in BCD, our decimal numbering system, and do what? Convert it over to binary so for my counters and all that other kind of stuff. So I could display the output of a counter, even though the counter's displaying in decimal up here, it's actually in binary. But I can take the output of a counter's accumulator and I can send it to now I can send it to a display that displays decimal for me, right? You understand that? Or I can send it so we're doing this all the time. So it gives us the ability to go between decimal and binary to decimal without using the calculator. It does it automatically. So y'all okay on those two instructions? Pretty neat, right? Yeah, I think that's about it for this chapter, ain't it?
The rest of the chapter is logic programming of it.
Are you leaving, Mr. Ellis? Okay. Just want to know. Oh, he left his book here. I didn't see that. I'm sorry. Yeah, I am. So what happened to my PowerPoint?
Hurry out of town this week.
No, I didn't.
You were on the last slide.
But I just want to drop back and read these. So what did we go over?
We were talking about the last part, the data.
Okay, so any questions on the move instruction?
Movement?
Just move. Any instruction, any questions on the move instruction? Pretty straightforward, right? Everybody okay with move with mask?
Yeah. Okay. Actually maybe.
Yeah, and mask, and it's an and mask, and what do we use and mask for? To make sure certain bits are cleared, right? You understand? So we strip off what we don't want.
There is no or.
There's no or. Well, we could use an or instruction to do an or mask, but there's no move with or. So what they've done with the move with and is we strip off bits all the time. Is they've included two instructions in what? With one, they've included two tasks with one instruction. Index addressing, everybody okay with that? Yeah, that's the way you specify, but it allows us to automatically go through addresses without us trying to specify all of them, right? It's used by a bit, it's used by your bit shift left, bit shift right. It allows you to use shifts of greater than 16 bits. We can shift left greater than 16. We can shift right greater than 16. We showed y'all that. It allows us a temporary storage location so we can save stuff on the stack. It allows the microprocessor, when we use a JSR, to do what? To automatically use the stack to save the program counter, the status register, so it can have ability to do what? To come back. We use it to fill. We use it to copy. So it's a very, very powerful addressing mode. First in, first out, last in, first out. Everybody okay there? Okay. Copy and fill. Everybody okay there? And then, of course, the 2 data conversion instructions that we have available to us. We can go from what? Binary to BCD, and we can go to BCD to binary.
And Mr. Russo, with the copy instruction, like, how often would you use that? How often have you used it? Like, we use the move more than we did the copy. Like, the move instruction.
Well, we didn't use it. It doesn't mean you will ever use it. It's just available for you to use. Okay, so understand, you can see the benefit of that. If I wanted to just copy a bunch of garbage from over here and do put it over there. It's just like what's going on with this video right here. So I'm dealing with 2 types of memory. I'm dealing with video memory and I'm dealing with program memory. Well, how does it get the information from the program memory over to the video memory? Just do a copy. It just takes it over here and it's just this what sends it to the video. So we have a lot of RAM in the machine that you don't realize what's going on.
So, you use copy, like how I was sitting there talking earlier about adding, like, to add, like, multiple sources. Like, say you got, like, multiple add instructions that have, like, a bunch of different things going, like B, C, D, 1, 2, 3, 4, and then you click copy and copy like another one, and it puts them all together.
Well, the problem is copy goes from consecutive addresses to consecutive addresses. So when you would have to remember when you did your math and stuff like that, you would have to put all your answers in consecutive addresses.
Yeah.
And then you could take all your adds and stuff and put them somewhere else,
Yeah.
right? And then maybe come back and reduce. Then you could come back and do what? You can come back and use this with different numbers and put them somewhere else. And then you can come back later on and say, okay, this was the results of the first run. This was the results of the second run because you kept up with this stuff every time. Okay. So understand I could use different addresses to keep up with different information. And instead of me trying to store them out there, I could just do what every time? Just copy them. And then I can reuse that memory because what did I do? We do that all the time. You know, a lot of times when I'm going to modify a program, this is a good idea to get into, especially in robotics, is make a copy of the program that's working, right? You do what and do what. And then you can edit the one, and if you screw it up so bad it's no good anymore, you can always go back to the one that was working and still be in business. So we do that all the time. I do copying all the time. And that's just taking information that you got here and doing what? Putting it there.
Yeah, I learned to do that after CC deleted my file.
Yeah. So you learn how to do that. So one of the things we teach y'all how to do in operation and programming is how to do what? Copy files. How to rename them, copy them. So, a lot of times when you copy them, you rename them to let you know that which one is the what, the original one and which one you're working on. And you need to get in the habit of doing that, guys. If you're programming, you need to get in the habit of doing that. Like I said, I was working on a program on this one, and it just blew out the whole program. It came up and it said you got a controller fault. It says it was a fatal fault, and my program was what? It was gone. Yeah, and this happened to several people over in PLC3. And you can see those big old programs where you got 4 subroutines and all that kind of stuff, and you enter that and you lose your tag table and everything else. And you have to go back and do what? So, that's why we call, so over there, when you get in there, we're gonna teach y'all the 10 run rule. So that way, if it blows out on you, because you're doing a bunch of stuff you've never done before, and all it takes is one click to screw something up, right? You understand? All you lose is what? 10 runs. You could always go back. So anybody who takes PLC 3, we do that in the summer, guys, and that's a really good class. Because you actually get to wire the PLC, and you get the ability to play around with the step 7 software to find out how they do it. Good gracious.
I think I'll be done with all my,
Yeah.
elected bill by then for the extra classes.
Have they put out a list of things they're gonna offer?
Yeah, it's out there already. Y'all should have got an email saying, that online registration
Go ahead.
Huh?
Go ahead and register.
for spring. Yeah. Okay, guys. If y'all want to hang around and talk, it's okay. I'm here to 9:30 anyway, so.
People like, hang around, talking, I'm like, I'm going to sleep. I'm tired.
Tucker had a date. So he had a priority interrupt.